Okay, so we've done a lot of work with base 10, right? And we wrote functions that go from a number to numeral, the numeral to number, and we showed that in fact those functions work correctly. So that if you convert a numeral to a number and get the numeral, you get back what you started with and so on. All right, that's all really nice. What about binary numbers? I mean, those are the ones that we really care about, right? Because those are the ones that computers use. And of course, you know, that's just like decimal numbers, except we use base 2, right? So here we have 12, okay? This is a number. Don't confuse that with the numeral, right? We cannot have the numeral 1, 2 in base 2, okay? Because 2 is actually equal to 2. And you can only use digits that are less than the base. So 1, 2, or 12 is actually 1 times 2 to the 3, that's 8, plus 1 times 2 to the 2, that's 4, and then we have 0, 2's and 0, 1's, okay? So yeah, that is in fact equal to 12, okay? So yeah, 12 is 1, 1, 0, 0 modulo 2, okay? Now, binary representation, if you don't have leading zeros, then it's also unique, okay? So the proof is identical, almost, right? It's almost identical to the proof that we did for base 10. So you should be able to do this. You should be able to take this and say, yep, that's true, okay? In fact, I want to go further than that. You should be do it for any base, right? Not just 2, right? So you should be able to prove this. For base B. Okay, make sure you do. All right. We also want the representation to, I mean, we have a function that does that, and here it is, right? So binary representation of 0 is nil. Binary representation of n is figure out what the representation is for n divided by 2, and then add the remainder in front. That's because it's built in it backwards. Okay, so yeah, that's a function that we should be able to write, and here it is, right? This is the exact same function as before, except is 2 instead of 10. All right. All right. And of course, we can go from a numeral back to a number. Okay. So if you have nil, then that's actually the number 0, right? If you have a list that starts with A and is followed by a whole bunch of stuff, then it's actually A plus 2 times whatever that bunch of stuff gets turned into when it's a number. Okay. Those are the equations that should be the case. These are the same equations that worked for base 10. Again, make sure that you understand these equations. Make sure that you can construct these. Okay, and once we have the equations, it's actually very easy to write the code, right? We just translate the equations into code, and as before, oops. Okay, as before, what we have is the test. Okay, so this is just this L equal to nil, right? In fact, we want to say not equal to, because we're checking for non-empty lists. And if it is, then we're in case 2, okay? And if it isn't, so that L is actually equal to nil, then we're in case 1. And we just put down the right-hand sides of those, and that's the end of the code, right? I need one if statement to tell me which one of the rows I'm in, and then I need to put the right-hand side of those rows as the value. Okay. I'm going to jump right into the theorems because this is all just like base 10, right? There's nothing new here. So let's go ahead and do the first theorem that says that if I take a number, I convert it to a list of bits, and I take that list of bits and I try to reinterpret it as a number, I get the same number. And when you do this, it just proves, right? This is the dream. Almost never happens. All right. So let's go in the other direction. I actually have a list of bits, okay? And the last element of that list is not equal to 0. That's because that's the leading element, okay? Then, if I take that list of bits and I translate it to a number, and then I take that number and I convert it to a list of bits, I should get back the original list. Not a surprise, this doesn't work, right? I mean, it didn't work with base 10. But at least we figured out the problems in base 10, so we'll just take those same theorems that we figured out for base 10 and include them here for base 2. And when we do that, it still doesn't work. Okay, it worked for base 10. Why doesn't it work for base 2? So what we have to do is kind of look at the checkpoints and figure this out from scratch. So let's look at the very first checkpoint. Okay, so we have here number to bits of And don't forget, car is just first, right? So car L is really basically just A naught, okay? And then bits the number of cooter L, this is rest, right? So I take bits the number of the rest of L, right? I convert that to a number, then I multiply by 2, and I add A naught. Hey, that really is the number that I start with, so number to bits should work, okay? Now, what's happening actually is this. It looks at number to bits, and it can't tell what that is, right? But you and I should be able to tell what that is, because that should be A, right, in front of numbers to bits of 2 times B, right? I mean, you know, intuitively, right? Because L is a list of bits. So that's what we have to tell it, right? It got confused. Again, what's happening is that there's some obvious fact that you and I can recognize and that ACL2 can't. So what we need to do is to tell it that fact, right? Number to bits of B plus 2 times n, right? That should be equal to something, right? So what should it be equal to? Well, if n happens to be 0, right, then if B happens to be 0, then what I have is just the total, 0 plus 2 times 0 is just 0. The number to bits will return nil, okay? So that's what's happening here, okay? Otherwise, it should just return the bit B. In fact, I know that it's 1, right, because it's a bit and it's not equal to 0. So that's what the second value is, right? So what's happening is I have to check, right? And that's simply because I made the decision that if I have a 0, right, instead of turning that into the list that contains 0, I'm returning just nil. That's because I really wanted not to ever have a leading 0. Okay. Now, suppose that that n is actually not 0, okay, but still a natural number. Then what I need to do is convert that to bits and then add B in front, right? Okay. Actually, if I'd ask you to kind of write this lemma down, I think you would have succeeded, but you wouldn't have written it like this, okay? You would have written something different, and that's okay. All right. The reason that I wrote it like this is because I know how ACL2 works when it starts to prove theorems. And so I actually write my theorems in a way that will help ACL2 use those theorems to prove things later. Okay. How does that happen? Years of experience. Okay. That's just, that's what I did for my PhD. That's what I've worked on for, I don't know, 15, 20, something, some ridiculous number of years. I don't expect you to get to that level of sophistication, okay, in this class, right? If you are interested in this and you want to pursue research, then by golly, you'll get this. It takes about 6 months to a year to learn ACL2. That's all, okay? However, what I do want you to do, and I want you to make a deep commitment to, is to learn whatever tools you are going to use at that level of sophistication, okay? Just get really good at whatever it is that you do. If that ends up being Angular for building web pages, then become an Angular expert. If that ends up being Microsoft Word, then be the best Microsoft Word user that anybody can possibly be. Expertise is a good thing. Whatever tools you pick, right? I mean, whatever career path you choose to take, by golly, actually learn how to use them really, really well. Anyway, enough proselytizing. Let's move on with this proof. Okay. So now after we add that lemma, like I said, I wrote it down very carefully. The proof does go through and it actually succeeds. Okay. Now, you might have a question at this point, which is, we did this for base 10 and we actually had those other lemmas and that was enough. Why do we have to add this extra lemma in this case? Okay, that's a really good question. All right. I'm going to give you the answer, okay, with a little bit of hand waving, and it's this. The way that ACL2 works is it looks at what you're trying to prove and it says, I have this theorem here, right? So I could actually prove this if I used that theorem, right? And, I could prove this if I used that other theorem, and so on, right? And so it takes what you start and it kind of rewrites it using the facts that it knows, right? And it just keeps doing that until eventually it finds true or a counterexample, okay? Now, ACL2 knows a lot about base 2, right? And why does it know a lot about base 2? Is because ACL2 is used very often to prove properties of circuits, and circuits are, work in base 2, is either on or off. So a lot of people have written lots of really useful lemmas for binary representation. And in this particular proof, as it went along, it went, oh, I can use this thing that somebody proved when they were trying to show that the Intel chip worked correctly in division, for example. And it uses that lemma, which it actually doesn't have for base 10 because nobody's ever needed it. So as the proof progresses, if you're in base 10, it goes along this path. If you're in base 2, it finds that lemma and it goes, oh, I should go along this other path, right? And that's why it gets stuck. Okay, so that's why we have to give it an extra hint, right? That's unfortunate, but that's the way that all systems work.